All right, chapter 14 is about ethers, epoxides, and thioethers. First thing, just to remind you what ethers are. Ethers have the general formula of some sort of R group, followed by an oxygen, followed by another R group, where your R groups can either be the same or they are different. If the two R groups are the same, it's a symmetrical R group. If they are not the same, if they're different, then obviously they would be unsymmetrical. This is just to kind of give you an example of just how you change the groups. Water's two hydrogens, alcohol's an R group and a hydrogen, ether are two R groups. Here's an example of a symmetrical ether. Probably the most common symmetrical ether is diethyl ether, which is used as a solvent. Here's a unsymmetrical ether where you have an aromatic ring and a methyl group. And this is a cyclical ether. A lot of ethers are cyclical, especially found in our natural environment. This is tetrahydrofuran is a solvent used very often in organic reactions. Very stable. Ethers are extremely stable. They're very non-reactive. That's why they are used as solvents a lot of the times. Section 14.2 talks a lot about the structure of ethers. Ethers are polar because you do have a bent shape to them. You have the two lone pairs and you have this bent shape. And the oxygen obviously is more electronegative, so it withdraws electrons from the carbon groups, making very partial negative on your oxygens here, and a partial positive. So here you have a partial negative charges on your oxygen, and on your carbons you have partial positive charges on your carbons. So therefore you have a dipole. That's what this is kind of showing, a dipole going towards the oxygens. Your oxygen is sp3 hybridized. It's a tetrahedral because you do have the four groups. Has a bent geometry. I just said that. The bond angle, we're not going to talk too much about this, is 110. Remember, in tetrahedral, your bond angles are usually 109.5. It's 110 just because of the lone pairs. Your bond angles aren't exactly, what they are, but it's pretty close. And your carbon oxygens are polar. Here's just some of the boiling points, just to kind of show you the difference between the boiling points, things of the same weight, with respect to the types of intramolecular bonding that it makes. All right, everything's always compared with water. Right, water is, it has one of the smallest weights if you compare it to this, but the boiling point is one of the highest, and that's because of the H bonding it does. So here's a great example. Ethanol and dimethyl ether. Same exact weights because the formulas are the same. All right. You have two carbons, 6 hydrogens, and an oxygen. And notice that the difference in boiling point is almost 100. All right. Your difference actually is about 103. Right there. You have a difference right here of about 103. And the reason, it's pretty obvious, is because you have a hydrogen bond on the alcohol, where on the ether you do not have a hydrogen bond. So because of that, the boiling point is much lower. Ethers do generally have a very low boiling points. Here's a good example of propane. All right, now propane also has about the same weight, but notice this is nonpolar. So now you have a nonpolar molecule. You have all the the London forces or the van der Waals forces. So you now have even lower than an ether. So you have a hydrogen bonding, you have a dipole, and then you have the van der Waals forces. And then they show you larger molecules. All right, they show you between the butanol, the tetrahydrofuran, the diethyl ether, and pentane. Again, has the same effect. What is interesting, if you notice the boiling points, the boiling point of the cyclical structure is almost twice as much of that as the as a straight structure, and that's because of something that we've talked about last semester when you're talking about more of van der Waals forces. Your cyclical structure, you have the same number of atoms, but a cyclical structure is a little bit more planar. So these molecules can pack on top of each other a lot better than they can in a straight chain. So because of that packing effect, you can technically form more of the van der Waals forces, therefore increasing the forces in your molecule, increasing the boiling point. So that's kind of a good example of showing that. All right, hydrogen bond acceptor. So the point in this one that they want to make is the acceptor. Ethers, if we just look at ethers, ethers do not have H bonding or hydrogen bonding. Sorry about that. Let me, I'm still trying to get used to this thing. Hydrogen bonding. All right, because you don't have a hydrogen. All right. However, however, ether does have a polar oxygen, so it can accept a hydrogen bond as long as there's a hydrogen in your solution. So if you throw in an alcohol or water, actually water won't be soluble in ether, but if you throw in an alcohol, you could still form a hydrogen bond. Okay, so the oxygen on the ether is what's called a hydrogen bond acceptor. It's not that ethers make hydrogen bonds. It accepts a hydrogen bond from a molecule that does form a hydrogen bond. All right, you have to have that hydrogen there in order to have the hydrogen bond. All right, so ethers can't hydrogen bond with other ether molecules, so their boiling points are lower than alcohols. We talked about that. However, ether molecules can hydrogen bond with water or alcohol molecules, but not really with water since it's not that soluble. Ether, though, does have a small amount of water, like all dissolved in it, so you do have a little bit of water in ether, but for the most part, water does not dissolve in ether molecules. And they are hydrogen bond acceptors. That's what we just talked about. Ethers are commonly used as solvents. That's one of their main things that ethers do. Diethyl ether we've used last semester. I believe when we did an extraction, we used diethyl ether. This compound, the 1,2-dimethoxyethane, is commonly used as an ether. Like I said, tetrahydrofuran, dioxane used as an ether. Ethers widely used as solvents because they can dissolve nonpolar and polar substances. Yeah, like I said, it's mostly inorganic, but the more oxygens you have on your molecule, so like on the glyme and on this one, they can actually act as a solvent for more polar molecules because you have more oxygens available for hydrogen bonding. And one of the best things is that they are very non-reactive towards a strong base. Also, strong acids, as long as you don't heat it, they will not react. They do form a lot of these complexes. This is kind of why they're used for Grignards. Your magnesium kind of gets stabilized by the ether. All right, you can see the ether solvents. The lone pairs kind of stabilize that magnesium. Remember, your magnesium has a plus charge. So you have these partial negative lone pairs that stabilizes Grignard reagents, organolithium reagents, helps to stabilize them. Here is our BH3, which we used in the anti-Markovnikov alcohol formation. And the solvent of choice is tetrahydrofuran. That's the short, is THF. So these are very common solvents used in these reagents. So the complexation of the ether with the Grignard reagent stabilizes the reagent, helps keeps it in the solution. Because remember, Grignards are polar. It's basically, remember, this carbon magnesium bond, your carbon has a negative charge and your magnesium has a positive charge. So, you know, in a way, and then your halogen right here is also going to have a negative charge. You kind of have, remember that your Grignard reagent is somewhat ionic. All right, so you have to have a solvent which can, you know, make can stabilize it as well as keep it in the solution. Electrophiles. So here our BH3 is acting as an electrophile. The ether's non-bonding electrons stabilize the BH3. All right. So you'll kind of see THF as a very common solvent in a lot of these reactions. All right. As far as naming, the common names for ether is very straightforward. What you basically do is you name the two alkyl groups attached to the oxygen and add the word ether. All right. So, and then you name the groups alphabetically. So let's just look at an example. So here's an example. Notice on either side here I have an ether group. I'm sorry, ethyl group. And I have another ethyl group on this side. All right, so I have two of the same groups, a symmetrical ether. So this would be called diethyl ether. Very straightforward. All right, let me erase this, get that out of the way. So that's called diethyl ether. Okay, sometimes people call it ethyl ether because if you just say ethyl ether, then that just implies, well, I have two ethyl groups on either side. Okay, if I have a non-symmetrical ether, you name it alphabetically. So notice over here I have a tert-butyl group or a T-butyl group. All right, T-butyl. All right, and then on this side I just have a methyl group. All right, so obviously the B alphabetically comes before the N, M, so this would be called tert-butyl methyl ether. Okay, now there are some people that have called it methyl tert-butyl ether just because the M comes before the T, but we've learned that the B is what you use alphabetically. So I don't like how your book is using this. I am going to cross this out and say just ignore that. It isn't an or. That's not how you name it. Okay, so if you have ethers that have two of the same groups on either, I'm sorry, that is very easy. If your groups on either side of the oxygen are very easy to name, like a methyl, ethyl, tert-butyl, isopropyl, a cyclohexyl, phenyl group, if they're easy groups, then this is the way that you name them. You just basically name each group alphabetically, followed by the word ether. If your groups are much more complicated, if you have a group, let's say you have a group here that has a chlorine coming off of it and an aromatic ring that's coming off of it, then you got to use the IUPAC way, which we will learn on the next slide.